a final algebraic varieties over an algebraic closed field. Okay, so I take a field. Do you know what is algebraically closed? We discussed this before. Every polynomial which is non-constant has a root in the field.
Yes.
So I will assume from now on, in these next 20 minutes, that K is algebraically closed. And if you want, you can suppose that K equals C. Now, I will take the ring of polynomials in n variables. These are formal sums. Such that these A, I are in K. This is a ring. You can sum polynomials, sum any term by term, multiplying with everyone versus everyone. And now let me take a family of polynomials. F1 up to Fn. Elements here, non-constant of course. The zero set of this family of polynomials are all the roots, common roots of these polynomials inside K to the n. Definition: the zero set of F1 Fn is the set P1 Pn in K to the n, such that Fi evaluated at P1 Pn equals 0 for I equals 1 up to m. So this is the zero set of the family F1 up to Fn, and it's still not a variety, just the zero set of a finite family of polynomials. So this just means that you are replacing x1 by p1 up to xn by pn. You are plugging the points here, and you are computing the result of this finite sum. And if this is 0, then you put that point there. If it's 0 for all the polynomials that you are considering. Now, another, you can also call this an algebraic set. Definition: a subset inside K to the n is algebraic if you can present it as the zero set of some polynomials. Now, you can use algebraic subsets of Kn to define a topology, which is called the Salinsky topology. So, what are the actions of closed sets of a topology? There are three of them, right? The first one is the total space and the empty space are closed.
Yes.
The second one, which one is it?
Union of any number of open sets is open.
Yes, but in terms of closed.
Finite union of closed sets is closed.
Thank you.
And arbitrary intersection of closed sets is closed.
Thank you. So again, finite union of closed sets is closed and arbitrary intersection of closed sets is closed.
Yes.
Those are an alternative version for a topology in terms of closed sets. What I'm telling you is that if you take the family of algebraic sets inside K to the n to be the family of closed sets, they are going to follow this action.
Yes.
This topology on K to the n is called the Zariski topology. Okay?
Yes.
So the affine space is the pair. Let me define it. Definition, the affine space and dimensional affine space or K affine space, if I want to specify the field, is the pair K to the n and the topology that I have just introduced. So this family of algebraic sets are the closed, so you can either define it as the closed sets or the complements are going to be the open sets. This is called the affine space over K, and it is denoted as A n. Why? Why not just Kn? Can someone tell me? Because Kn is a set. Kn together with the Zariski topology is a topological space. Now they are not the same. So this is a topological space. This is why we call it the affine space, because it is a set with a topology. But K to the n is just a set. It is very important to do the distinction. Let's compute the Zariski topology of K1. Or to fix ideas, let me put here C. Okay, so what are the closed sets here? By definition, I take the complex plane and a subset of the complex plane, let me draw it. X is closed if and only if I can find a family of complex polynomials such that these X are precisely the common roots of this family. Again, this X, big X that I draw here is going to be algebraic or a closed set in the Zariski topology if and only if I can find a family of complex polynomials which vanish in this set. Let's write that. Yeah, perhaps I will erase here. So, X is closed. But in a course of algebraic geometry, one can show that instead of families or subsets of polynomials, you can take the idea. So the zero set of the family is the same thing as the zero set of the ideal. What is an ideal? Do you know what is an ideal? Okay, so if R is a ring, an ideal, or let me take a subset of R, in this case is T. The ideal generated by T is by definition the finite sums of all linear combinations of elements of T with coefficients in R. So, ideals is a generalization of linear span of a vector space. It's like taking finite linear combinations, but you are allowed to take elements which are coefficients in your ring, and the elements Fi should live in the family that you are computing the ideal. So, using this, which I can prove, this property that it is the same thing to compute the zero set of a family than the zero set of the ideal. In fact, it's not hard to show it. So if you are interested in algebraic geometry, you should this exercise. If not, then you are spared to it. So I just need to check if it is the same to check for families and to ideals. I just need to check this for ideals. And now I use commutative algebra. C of x is a principal linear domain. Again, in fact, this is a theorem. If K is a field, this is a theorem. If K is a field, then K of x is a principal linear domain. That means that any ideal is spanned by a single element. So an ideal here is the same to take a single polynomial. We are done. Because after some algebraic manipulation, we see that closed subsets in A1C are roots of polynomials. And every polynomial has a finite number of roots in C counting multiplicity. So closed sets here and finite sets. Is it clear?
Yes.
So what is the topology in terms of open sets? The complement of finite sets are infinite sets because C is infinite. So the open sets are the complement of the closed sets. If the closed sets are finite sets, then the open sets are infinite. And that's called the cofinite topology.
Yes.
So A1C is C. The Zariski topology is equal to the cofinite topology. in which an open set is an infinite set, the empty set, or the total set. And you can see that this is what we call a very coarse topology, not fine topology, because open sets are very big. Let me illustrate that. So we take the complex plane and let me draw an open set. In order to do that, I just need to exclude a finite number of points, right? Let me take away these 3 points from the whole complex plane. So the open set U is all the complex plane, let me call this A, B, and C, minus A, B, and C. Let me take a look. Any open set, I just authorize to take away a finite number of points. Maybe I take away C again, or A prime, B prime, and B. This is an open subset, which I will call B. Now, if I want to intersect U and B, since this is a finite number of open sets, it's going to be open. And the result is just the whole plane without the points that are in there. Right? But the problem with this topology is that the open sets are very big. It is not as the classical analytical topology or the metric topology that we have in C, in which this small disk, let me say the disk centered in Z and of radius R, open disk, which is just the complex numbers W, such that the metric between Z and W is smaller than R. This is an open set with respect to the Euclidean topology, and it is very small. I can do this R as small as I want, such that I can always take one small ball inside another. So the Euclidean topology is very nice because you can modify your open sets to be as small as you want. But the Zariski topology does not have that property. The Zariski topology, if you have an open set and another open set, I challenge you to find two open sets that have empty intersection. So in the analytic topology, it is very easy, right? I take this distance, if the distance between the centers is smaller than the radius, then the intersection of these two disks is going to be empty. Can we do the same for the Zariski topology? The answer is no. But I need you to be combined by that. So suppose that there exist two non-empty sets, open sets, such that the intersection is empty. Let's make the exercise. Suppose that I find an open set here, which is C minus a finite set, and another one here, which is B, C minus an open finite set, and a finite set G, such that the intersection U inter B is empty. So I can use the language of set theory. For example, here this is C, intersection F complement, or maybe I can go to, yes, sorry. If I take complements here, what do I have? I have that they complement here, they complement here. This is complement of U, union, right? Complement of V. And the complement of the empty set is the fourth set. But from here, I see that the complement of U is finite. And the complement of V is finite. So I am saying that C is finite, which is a contradiction.
I think this is the same argument which we used to prove that cofinite topology is not Hausdorff.
Yes, thank you. So technically, we see that this space is T1 in terms of actions of separation.
Yes.
This space is T1, but it is not T2.
Yes.
Okay, so what I wanted to do here is to combine yourself that the topology is very coarse. It is not possible to do what we do in analytic topology. It is open sets are very, very big. So any two open sets are going to intersect. This is the statement. But so I already introduced the topology. Let me introduce what is an affine variety, and we will be done with algebraic geometry, and we will pass to topology. And I will finish the lecture with that. Okay, so what is an algebraic variety? Definition: affine algebraic variety. Let me be not so technical, and let me define it just as a closed algebraic subset. This is not a good definition, but I don't want to torture you with more algebraic geometry. So closed algebraic sets are algebraic varieties for us. So if I have a closed set, I can induce the subspace topology, right? So I have a subset X inside AN. Since this is a topological space, I can consider this with the endo topology, and I will have here a topological space, right? So algebraic variety, we consider it with the sadistic topology. Example. Let me put here R just to see the picture. So this is the polynomial xy. This is a polynomial in R xy. And the variety is the zero set of this polynomial. So if I compute it, this is just the first PQ in R2, because I am over R, such that PQ equals 0, right? But this tells me that either the first coordinate is 0 or the second coordinate is 0. So this is the union of the two coordinate axes. The picture of X inside R2 is the coordinate axe y equals 0, and the coordinate x equals 0. And what is the subspace topology? What we see the picture, but I want the topological space. Can you see the topology on this variety? So, let me go to the complex non-terms to work better. This ring has dimension 2. This means that the ideals that I can consider here are either A0, 1, or 2. So, just to spare you the technical details, this means that basically all the closed sets are generated by curves. So basically, a closed set inside A2C is the zero set of a polynomial in two variables. And a polynomial in two variables is a curve. So, what is a curve like? This is a closed set. So, the intersection, in most cases, of two closed sets is a finite set. By this, I want to convince you that the topology in X is almost the same as in the line, which is the cofinite topology. So, maybe you have studied differential geometry. Differential geometry, one of the favorite curves is the ellipse, which is something like and in differential geometry, maybe we can consider this as a curve inside R3. We are interested in local conditions such as curvature, maybe a Fermat-Serret system, maybe compute a normal or a tangent plane, different aspects of the geometry of contact of this curve. But many of these arguments are local. For example, if I want to measure the curvature of the ellipse here, I just need to focus on a small ball. I just need to draw a small neighborhood here and analyze what happens around this small ball. Imagine that I have a smooth curve here in the plane, like this white one. Maybe I can do the same. For example, I get myself into this point and I want to study the local properties of the curve around that point. So, if you haven't discovered the problem yet, the problem is that I cannot do this in the algebraic geometry. Why? Because I need to use the Zariski topology. And in the Zariski topology, this small neighborhood is not an open set. Again, all the differential geometry and physics that we learn with respect to the Euclidean geometry. Tangent planes, normal vectors, forces, differential equations, motion, vector fields. Everything is linked to the Euclidean topology. There are other geometric objects, such as those appearing in algebraic geometry, which may be of the same nature as these objects. For example, an algebraic curve. Let me give you a smooth algebraic curve, real, so that you can see an actual object instead of just ideas. So let me compute a cubic for you. This is one of my favorite cubes.